Are you here?
Yes, sir. I'm ready to go.
Good. So now, next topic, limit of a function. The first slide is devoted to the so-called related delta neighborhood. It is usually denoted in Russian literature as capital U with a circle, and the deleted neighborhood of a point P is a neighborhood of P without this point P. So you see the mathematical definition of this neighborhood is such that all that we have all x such that x minus p absolute value of is strictly greater than 0 and less than delta. So you see the first inequality is very important because we cannot take x equals p. Is it clear?
Yes, it's clear.
So
Yes.
related delta neighborhood. Here you have an example. So if I take a deleted neighborhood of my point,
Excuse me, sir.
yeah,
I don't understand.
you see, Onya,
Yes.
the problem is you have, as in this example, I take the interval between -1. Here it is not, it's a misprint. Between -1 and 1. You see a
Mhm.
misprint.
Yes.
So excuse me. So y here is between -1 and 1. And I say that I want to take a deleted neighborhood of my point 0.
Yes.
So uh, because of this misprint, I have to write that it will be the union, of two open intervals, -1, 0, and 0, 1, but without my point 0.
Um. Okay.
So here, excuse me, I will check this in the next version of this file, but in fact, you see, if I take a neighborhood of a deleted neighborhood of some point P, then I will have the neighborhood, but without this point P.
Ah. Okay. Understand.
Okay? Clear?
Yes. Thank you. Yes.
So excuse me for my misprints because
It's okay.
it is possible. So now, as for the Cauchy and Deine definitions of the limit, my favorite definition is Cauchy definition. So we say, due to this definition, we say that L is a limit of a function as x goes to p if and only if for every epsilon positive there exists delta which depends on this epsilon such that the absolute value of f of x and L, the limit, is less than epsilon whenever x minus p, the absolute value of x minus p, is less than delta and greater than 0. You see, here we have a little problem. Why? Because maybe we have a limit of my function at the point P. So as x goes to P. But I do not know, I have nothing, I have no information about the existence of my function f at this point P. You see, it will be possible if my function f will be continuous. But now I have only this, that the limit maybe exists, but I don't know what is the limit, or I don't know. Can I say that my function is defined at this point? That is why, you see, we have to make use of this deleted neighborhood. That is why I write that the absolute value x minus p is strictly greater than 0. Is it clear, at least for the moment?
Yeah, for the moment, it's clear.
Yes.
Yes. So,
Not very clear.
Valentina, not very clear?
No, I misunderstood a little. I don't understand very well.
Well, Valentina, please say me where is the problem for you? You see, can you imagine the function which is a constant, for example, up to x equals 1. So
Yeah.
then, as x equals 1, for example, the constant is 1 also, okay? So as for the point x equals 1, I say that my function is such that f of x is 2. So you see, first of all, up to x equals 1, you have always 1, but as for x equals 1, you have that your function is defined by 2. You see?
Yeah.
So as for the limit, I can find the limit for this function. It will be 1, but it will be not the value of my function f of x at this point x equals 1. The limit exists, but
Yeah.
Valentina is clear.
Yeah. Now it's more clear.
More clear. So you see that here we have a problem between our usual functions. We know these functions: x square, x cube, exponential function, log, and so on and so on. But there is a very great number of functions which are not so good. So in order to deal with these functions, the first step is to introduce the definition of the limit. As in my example, for this very simple function, which is a constant up to, for example, x equals 1, but as for the point x equals 1, the value of this function will be 2. So from one hand, you have that the limit as x goes to 1 exists, but the value of this function does not coincide with the limit of this function. The value and the limit are different things. You see? Valentina is good. Take your pen and try to have a figure, to have your function. Clear or not?
Yeah, it's more clear.
Well, we will see in future. I hope that it will be more clear on that. So now the second definition. Usually in the English literature, you can find the sequence definition of the limit. So it is due to Heine, and it reads, a function f has a limit L at the point x equals phi if for every sequence x sub n where x sub n belongs to this dilated neighborhood of your point phi, which has a limit, the sequence f of xn has a limit L. So you see the idea. I take a sequence which is defined in this dilated neighborhood. So for any xn, xn is different from p. You see, then xn, any sequence, goes to p. And I say that if the limit exists, then the sequence of f of xn is L. So we are dealing with two sequences of real numbers, not with epsilon delta as in Cauchy definition, but with usual sequences of real numbers. Maybe for you it will be better to understand the situation. So for every sequence which is such that, first of all, the sequence belongs to the dilated neighborhood, you see, if the first terms, don't forget about this, if the first terms of your sequence, maybe, but the finite number of the terms belong to this sequence, we can forget about. We are dealing with an infinite number of the terms. You see? So I take any sequence x sub n, which is convergent, and the limit of this sequence is t, and for any of this sequence, I have to have that the sequence of f of x sub n has the same limit, which is L. Is it clear, or I have to repeat in other words?
It's clear.
Really?
Yes, Professor, it's clear.
Okay. So in your lectures, you have to know that these two definitions are equivalent. it is not our business, so we will go to this picture. You see, what do we have? Maybe it is not very good picture, because you see in this picture we have really a continuous function, but here we have something like the neighborhood of my point P, and consequently the neighborhood of the values of my function f of x, the neighborhood of the limit capital L. As here you see, I repeat, here we have a continuous function that then we have in fact no problem. But if we take something which is more sophisticated, we will see the same picture, but we cannot write that f of p is L, like in this picture. Here we show only the intervals, our deleted neighborhood of the point P and the neighborhood of our point L, capital L. Is it clear? Onya,
Yes, it's clear.
good. So now let us try to use this definition, the Cauchy definition, the first exercise, using the epsilon delta definition of limit. Show that the limit as x goes to 3 of 3x minus 2 is 7. So, due to the definition, we take epsilon, which is strictly positive, in an arbitrary positive number. So, here, we can choose our delta, which depends on epsilon. Immediately, we say that delta will be epsilon over 3. But now we will see how to find this delta in fact. So
Yeah,
we do not.
you can put wherever that if you want, or how to choose the delta.
You see, Valentina, do not read the first line of the proof, okay?
Okay.
So we go to this to the second, line. So I take f of x minus L, absolute value of. Our L is 7. Agree?
Yeah, agree.
Then 3x minus 2 minus 7, it will be 3x minus 9. So it will be 3 minus absolute value of x minus 3. Then I take that it will be less than x minus 3 have to be less than delta, okay? Because we are looking for the limit as x goes to 3, your p in the definition.
you multiply 3 because this is the limit, yeah?
No, stop. 3 is the limit as x goes to 3, you see? But 3x minus 9 is 3 multiplied by x minus 3. Agree?
Yeah.
Yeah. So we keep 3. We don't touch 3. But x minus 3, the absolute value of x minus 3 have to be small, have to be less than delta. Okay? In the framework of our definition. Mhm. Agree, Valentina?
Yeah.
Agree. So 3, it's from you see from our function. It comes from our function. It can be 4, 5, I don't know what. So if I take my delta,
For example, if the limit is x tends to 5, so is delta multiplied by 5?
no. You see, if x goes to 5, then you can calculate that 3 multiplied by 5 minus 2, it will be what? It will be 13, yes?
Yeah.
So you have to recalculate your limit, and you will see that it will be maybe another term. Will be another term. So 3x minus 2 minus 13, it will be what? It will be, in this case, 3x minus 15, 3x minus 15, then you will have that it will be also 3x minus 5, yes?
Yeah.
So your estimate will be 3 multiplied by delta, not by 5, but by,
Oh, okay.
you see, it comes from the function. If you change your function, you will obtain another coefficient if you want. Mhm. Okay?
Yeah, okay.
So you see, I have 3 delta. Then if I take delta equals epsilon over 3, in this case, you take delta which depends on epsilon. You see?
You need that epsilon in 1, yeah? 1 multiplied.
No. Valentina, I take an arbitrary positive number, epsilon. You see, I want in the framework of my definition that the absolute value between my function and its limit have to be smaller, have to be less than epsilon. Okay? And then due to this epsilon, because in fact, what do we have? We have that the absolute value between f of x and L is less than epsilon, but epsilon can be 1 over 2, 1 over 3, 1 over 100, 1 over 1000, and so on. You see? But it is a strictly positive number. So what do we want? We want that the absolute value between the function and its limit have to be, if you want, roughly speaking, arbitrarily small, less than epsilon. You see? And then I have to find my delta, which depends on epsilon. So I have to find the interval of my argument of my x. You see, as in the previous picture, x belongs to the interval p plus delta, p minus delta. So, for example, in this case, you see, absolute value of x minus 3 is less than delta, then x belongs to the interval 3 plus delta, 3 minus delta. Agree?
Yeah, agree.
So, in this case, in our case, the last line of this exercise, if I take, you see, if I take delta like epsilon over 3, then I will have that the absolute value of the difference between my function and its limit, capital L, will be less than epsilon. Then, you see, we have a number, an infinite number of epsilon. So we say that epsilon is an arbitrary positive number. So it can be very, very small as you want. And for any of these epsilon, I can find my delta. And the formula for this delta, our choice is delta equals epsilon over 3, as we say in the beginning of this exercise. Is clear?
Yes, it's clear.
Onya, ça va?
Oui, ça va.
Yeah. Ça va? Good. So, the next exercise, we will try to deal with another function. You see, maybe, maybe. So, let's suppose that our delta is 1. Then, in fact, why we say this? Because, in fact, we can choose. It is roughly speaking, but we can choose any neighborhood of our point 2. For example, we take delta equals 1. Then I have to find an appropriate estimate for the difference of my function x squared and the limit 4. So you see, I take, as in the previous example, epsilon strictly greater than 0. And what I want is to obtain the inequality x squared minus 4 less than epsilon. We know that a squared minus b squared is a minus b multiplied by a plus b. So we have to find the inequality x minus 2 multiplied by x plus 2. As for x plus 2, we see that it is not necessary to keep the absolute value. Then finally we have absolute value of x minus 2 multiplied by x plus 2. Then from the first inequality, you see, I say that x minus 2, absolute value of x minus 2 is less than 1 and greater than 0. Then x minus 2 is less than 1 and greater than minus 1, strictly greater than minus 1. Yes? Then x is between 1 and 3. So x is less than 3. Agree?
You can repeat?
Yes.
Yes.
Yes. Yes. So you see, we consider the inequality. Absolute value of x minus 2 is less than 1. Then we can open the absolute value and we will have that x is between 3 and 1. Yes? Agree, Hussein? Agree?
Yes, yes, Professor, I agree.
Yes, very good. So for our exercise, we have that x is less than 3. So finally, we want to find something like delta from the inequality 5 multiplied by absolute value of x minus 2 less than epsilon. You see, the important thing here, if we have this inequality 5 multiplied by absolute value of x minus 2 less than epsilon, then we return to the very beginning. If it is true, then the absolute value of x squared minus 4 will be also less than epsilon. Agree?
Yes, I agree.
Agree. So you see, you see that in fact we have the inequality. Absolute value of x minus 2 is less than epsilon over 5. Now we can find our delta. It was supposed that delta is 1, but maybe it is better to say that delta is less or less than or equals 1. So next slide shows us we have to choose the minimum between epsilon over 5 and 1. So if I take my delta, if I take epsilon rather small, you see, rather small, 1 over 10, for example, then if I take the absolute value of x minus 2 less than epsilon over 5, I will have that the absolute value between x squared and 4 will be less than epsilon. Agree?
Yes.
Yes, I agree.
Agree. So you see, due to the definition of the Cauchy definition of the limit of x squared as x goes to 2 is 4. Now let us consider another example. You see the exercise using the Cauchy definition. It is intentionally, I say here, not epsilon delta definition, but also Cauchy definition. It's for you. It is an equivalent notation for this definition, so you have to know both the epsilon delta definition of Cauchy definition. So the question is to find the number delta corresponding to epsilon given with the following limit. The limit as x goes to 7, square root of x plus 2 equals 3. And we take here, we prescribe, if you want, that epsilon is 0.2. So you see, we say always for any epsilon, for every epsilon, strictly positive. For example, if you have a question, if we take a fixed epsilon, what will we obtain? So here we have the corresponding exercise. Then you see the absolute value of f of x minus 3 is less than epsilon if the absolute value between x and 7 we take our limit as x goes to 7 is less than delta. Then you see that we have if we take epsilon 0.2, then we have that our square root of x plus 2 is between 2.8 and 3.2. I hope it's clear. Agree?
Yes, I agree.
Good. So now we take the square of all the parts of this inequality and we obtain that x plus 2 is between something which is written here in this slide. Then we can find that x in this case is between two real numbers which are written here. And finally, we want to find delta corresponding to this epsilon. So I want to consider the difference between x and 7 because x goes to 7. So we have that x minus 7 is between 1.24 and minus 1.16. This, you see, minus 1.16 is greater than minus 1.24. Agree?
Yes, I agree.
So the absolute value, due to the definition of the absolute value of x minus 7, the absolute value of x minus 7 is less than 1.24. Then you see, if I take delta 1.24, then the initial or original inequality, the absolute value of f of x minus 3 will be less than 0.2, that is less than epsilon. Agree?
Yes.
Onya, est-ce que c'est clair?
Oui, c'est clair. Très clair.
Merci. Mhm. So now in the next exercises, we make use of the definition of a limit at x goes to plus infinity. So before, we are dealing with a finite number, something like x goes to a maybe 1, 2, 3, 75, or something else. So a real number. Now we will use the definition of a limit at infinity. So here in this slide, we say that the number L, capital L, is called a limit of my function f of x as x goes to infinity if for every positive epsilon there exists n, which depends, capital N, which depends on epsilon, such that the absolute value between f of x and L is less than epsilon for any x, absolute value of x, because you see why we write absolute value of x, because x can go to minus infinity also. Not, you see here in this definition we have no sign of infinity, plus or minus infinity in general, if you want. So whenever the absolute value of x is greater than n. Is it clear? At least.
Yes, this is clear.
You see, for example, if you take the function 1 over x, okay? You take the function 1 over x. If you imagine the graph of this function for large x, it will be near 0, near the x-axis. Can you see this graph? Thank you.
I'm sorry, Professor, could you repeat the question?
Yes, the question is, if I take, let's take the function 1 over x. F of x is 1 over x, okay?
Yes.
And we studied the behavior of this function as x goes to infinity. You will see that as x to plus infinity, in addition to plus infinity. So you will see that for any epsilon, the difference between my function and 0 can be done smaller and smaller if I take x greater and greater.
Yeah.
Yes. So in the framework of this definition, I can say that the limit of my function 1 over x as x goes to plus infinity is 0.
Yeah.
We have to prove it, but you can imagine if you close your eyes and imagine the graph of this function, you will see that it's true. Agree?
Yeah.
Yes, I agree.
Agree. Very good. So now we turn to another exercise. So the exercise is as follows. We have to prove that the limit as x goes to plus infinity, here I think to infinity, of x plus 1 over x is 1. So in our future work, you will see that in order to, it is a remark which is not important for the moment, but I think you have to know. Here you have a fraction like x plus 1 over x, and x goes to infinity, maybe to plus infinity, maybe to minus infinity. It's not very important. So in order to find the limit without this epsilon delta argument, you have to choose the largest term, the largest power, if you want, in this fraction, and then you have to divide the denominator and numerator by this largest power. In this case, the largest power is x, or if you want, x to the power 1. It's the largest term here. 1 is a constant. So if I divide the numerator and denominator by x to the power 1, I will have the following form of my fraction: 1 plus 1 over x. And as in the previous example, 1 over x goes to 0. So this limit will be 1. But it's a comment. For the moment, we will use only the definition of our limit. But is it clear the idea of my argument?
Yeah, for me it's clear.
Very good, David.
Yeah.
So if you have, for example, if we want to discuss the limit as x goes to infinity of the fraction x cubed plus 1 over x cubed, we will have 1 plus 1 over x cubed, and the limit will be also 1. You see? Yeah,
Yes.
Valentina.
Yeah, it's clear.
Yeah, very good. So we take, as in the previous exercises, we take epsilon greater than 0, and what do we want? We have to prove the limit is given, is already given. So we have to apply our definition. So we want to have that x plus 1 over x minus 1, the absolute value of this difference have to be less than epsilon. This leads to the following inequality. The absolute value of 1 over x is less than x. I repeat for you why we write here the absolute value of 1 over x. Because we do not say, we can say that x goes to plus infinity or x goes to minus infinity. That is why we have to write the absolute value of this fraction. So now we can choose a number n, capital N, which depends on epsilon, such that the absolute value of x is greater than n. Now we can find that our capital N is in fact 1 over epsilon. Then if absolute value of x is greater than 1 over epsilon, then the difference between our function and the limit will be less than epsilon. And the limit 1.1 is true. Agree?
Yes.
Really? No problem. Hussein, no problem.
Oh no, I don't have any problem. It's pretty clear to me.
Good. Valentina, it's clear. Excellent. Mikhail, is it clear? Mikhail Robinson, is it clear? Thank you. So now the next slide is to show you this function x plus 1 over x, and we see that this function goes to 1 as x goes to plus infinity or minus infinity. This line, it's for next year, this line is a horizontal asymptote of this graph, but it is not important for the moment. So the next slide, the next exercise is to find the limit as x goes to infinity of 2x minus 3, or not to find, but to prove that the limit of 2x minus 3 over x plus 1 is 2. So as usually, we take epsilon positive, and we have to find a number capital N of epsilon, so such that for any x greater than n, we have the following inequality. So 2x minus 3 over x plus 1 minus 2 less than epsilon. So we rearrange the terms, and we have finally that this leads to the inequality absolute value of x plus 1 is greater than 5 over epsilon. 5 over epsilon. Here maybe it is a misprint, so I have to write x goes to plus infinity. So I have to change. I will mark for me. x goes to plus infinity, that is, our x is positive, then we have that x is greater than 5 over epsilon minus 1. And in this case, we can set capital N as 5 over epsilon minus 1. Then we will have that the absolute value of 2x minus 3 over x plus 1 minus 2 will be less than epsilon for all these x greater than n. So you have to note that in this case, the misprint is in the formulation 1.2, x goes to plus infinity. I will change this, and the next version of my file. Questions? Questions?
No, I think it's clear.
Valentina, clear?
Yeah, it's clear.
Okay, it will be enough as for the slides, as for our slides for today. So now we can discuss a little my question. So the question is, I have, you see, the sequences. So I have two sequences, x sub n and y sub n. For example, x sub n is a convergent sequence and y sub n is a divergent sequence. What can we say about the sequence x sub n plus y sub n? The ideas. It
It's
was,
converge.
huh? Louder, Valentina.
I think it's converge.
Converge. No, it's wrong. So, other ideas. You see, for example, Valentina, the simplest example. I have my xn, the convergence sequence, as, for example, 1. It's a constant sequence, yes? So it converges to 1. Agree?
Yeah, agree.
And y sub n will be minus 1 to the power n. It is a divergent sequence. Agree?
Yeah, I agree.
So if I take a sum, it will be 0, 2, 0, 2, 0, 2, and so on, so on. So in this case, we have a divergent sequence. Okay. So I think that the sum of a convergent sequence and the divergent one will be a divergent sequence. So the proof, try to understand. You see, I have Zn by the definition x sub n plus y sub n. If I assume that, as you, Valentina, I assume that Zn, the sum of the sequences, is a convergent sequence. Okay? Then I rewrite that this quality in the following way. y sub n is z sub n minus x sub n. Same thing, yes?
Yeah.
Yeah. Then you have that by your hypothesis that z sub n is convergent, x sub n is convergent, then the difference of two convergent sequences is a convergent sequence by our limit theorem. Yes?
Yes, I got it.
But y sub n by our definition, by our supposition, is divergent. So it is not possible. So your sequence z sub n, which is x n plus y n, is divergent. Agree?
Yeah, agree.
So now, if you want another question, try to think about, and we will discuss it next time. It is always on the sequences. You see, do you want this?
Yeah.
Okay. So please take your pens and write. I say, I have that the limit as n goes to infinity of the product x sub n multiplied by y sub n. And this limit, this limit is zero. This limit is zero. Okay?
The function x sub
No,
n
it's not.
is
No, Valentina, it's not a function. You have two sequences, x sub n and y sub n. And the limit
okay.
of the product is zero. Okay?
Okay.
So can we say, it's a question, that in this case, the limit of xn equals the limit of yn equals zero. Is it right or not? So if I have that the limit of the product xn yn is zero, can I say that the limit of xn is zero and the limit of yn is also zero? What do you think about?
All these limits tends to infinity?
No. The limit, Valentina, you have that the limit of the product of two sequences is zero, but n goes to infinity.
Mm.
No, it's not a function. It's not a function. It is really a sequence of real numbers. Understand? Eric, is it clear? The question.
I believe so. I just need
So-
to be able to.
I repeat, Eric. Well, can you repeat me the formulation of the problem? Your version.
I can repeat. I think that
Yes.
I write is the limit of the product x n multiplied by yn is 0.
Yes.
And if I can say that limit of xn and limit of yn is 0.
Is it, you see, can we say this?
Yeah, if we can say
where is
that,
the,
if it's
you see,
possible.
Valentina, where is the question? Is it right or not?
Yeah, it's right or
Is it
not.
right? Is it, you see, if you take two sequences such that the limits are 0, it will be evidently 0 for the product. But is it always like this? So can we say that the first statement implies always that the limit of xn and yn are 0? Here is the question. You understand?
Yeah, I got it.
So I think that next time we will discuss this example. Okay?
Okay, Professor.
So thank you very much. Have a nice evening. See you.
Oh, you too, Professor. See you
Thank
later.
you,
Thank you.
Thank you. See you.
Ciao, ciao.
See you.
Michael. Ciao, ciao.